The Solow model, as we developed in Chapter 8, shows how saving and population growth determine an economy's long-run capital stock and level of income per person. This chapter introduces technological progress to the Solow model to explain the steady-state growth in income per person. So in this chapter, you will learn how to incorporate technological progress in the Solow model, about policies to promote growth, and about growth empirics, confronting the theory with facts. In the Solow model of Chapter 8, the production technology is held constant, income per capita is constant in the steady state. However, neither point is true in the real world. For example, from 1900 to 2016, the US real GDP per person grew by a factor of 8.58, or approximately 1.9% per year, and examples of technological progress abound in real life. For example, US farm sector productivity nearly tripled from 1950 to 2012. The real price of computer power has fallen an average of 30% per year over the past 3 decades. In year 2000, there were 301 million internet users and 740 million cell phone users in the worldwide. But after 16 years, in 2016, there were 3.4 billion internet users and 5.0 billion cell phone users worldwide. In 2001, the iPod capacity was 5 GB, and you can have approximately 1,000 songs saved in iPod, which was not capable, of course, of playing episodes of Games of Thrones, for example. On the other hand, by 2018, iPod Touch capacity went up to 64 GB. That means approximately 30,000 songs can be stored, and you can play episodes of Games of Thrones, for example. So you can see in real life, there are lots of examples of technological progress you can find. Now, with that note, let's learn how technological progress can be incorporated in the Solow model. Here, we add new variable, that is, capital letter E, which is defined as labor efficiency, and assume that technological progress is labor augmenting. That is, it increases labor efficiency at the exogenous rate G, where G equals to change in E over E. We now write the production function as y equals f of k and L times E, where L times E is the number of effective workers. Here, increases in labor efficiency have the same effect on output as increases in the labor force. This seems harder to work with than before, but there's a neat trick to reduce the work. Let's see. Next slide. The trick is to express y in per effective worker terms, a mathematical device to make the model tractable. So now, let's define lowercase y as y over L times E, and define it as output per effective worker, and lowercase k as capital divided by L times E, define it as capital per effective worker. Then, the production function is now expressed in terms of per effective worker. Therefore, lowercase y, which is output per effective worker, is a function of lowercase k, capital per effective worker. And saving and investment per effective worker is expressed as S times y equals to S of f of k, all lowercase letters. So the only thing that's new here compared to chapter 8 is that G times K is part of the break-even investment. That is the amount of investment necessary to keep, in this case, capital stock per effective worker constant. And it consists of delta K to replace depreciating capital, N times K to provide capital for new workers, and G times K to provide capital for the new effective workers created by technological progress. So it is important for you to remember that here lowercase letter k is defined as capital per effective worker, that is k over L times E, And that means technological progress increased the number of effective workers at the rate G, which would cause capital per effective worker to fall at a rate G, other things equal. And the investment equal to G times K would prevent this. And this is the equation of motion modified to allow for technological progress. And here the plot looks like this. Compared to chapter 8, the difference is now everything is expressed in terms of per effective worker term. So horizontal axis is here lowercase k is defined as capital per effective worker, that is k divided by L times E. And investment and break-even investment are all defined in terms of effective worker terms. So are functions of capital per effective worker, that is. So if you plot them, the equation looks exactly the same as before, but the only difference is the definition of K. So, and also break-even investment has G added to delta plus N. But the way to find steady state is identical. That is, when these two curves cross, then that's the point of K star that represents the capital per effective worker at the equilibrium point. Now this table shows each variables and the steady state growth rate of each variables. For example, capital per effective worker is defined as lowercase k equals to uppercase K over L times E. In this particular case, at the steady state, the growth rate is 0. And output per effective worker is defined as lowercase y in this chapter, and that should equal to y over L times E. And also at the steady state, because it's a function of lowercase k, so at the steady state, the growth rate is 0 by definition of steady state in this case. But here, output per worker is actually growing because, as you can see, output per worker is capital Y over capital L. And if you rearrange the definition, that should equal to lowercase y times E. And since Y grows at the rate 0, it doesn't grow, but E grows at the rate G, therefore, at steady state, output per worker actually grows at the rate G. And total output Y is actually expressed as output per effective worker times E times L. And since output per effective worker doesn't grow at the steady state, but E and L grows at the rate of G and N, total output Y actually grows at steady state at the rate N plus G. So these are the main differences between this chapter's model and the previous chapter's model. That is, first, output per worker actually grows at the rate G, and total output grows at the rate N plus G. Now let's figure out the golden rule with technological progress incorporated. And to find the golden rule capital stock, you want to express C star in terms of K star, and C star equals to Y star minus I star, and investment in the steady state, I star equals break-even investment. Therefore, you can replace I star with delta plus N plus G times K star, and you can replace Y star with F of K star. So now C star equals to F of K star minus, open parenthesis, delta plus N plus G, close parenthesis, times K star. And C star is maximized when NPK equals to delta plus N plus G, or equivalently, NPK minus delta equals to N plus G. So I'm going to show the work during our Zoom session, but what you found here is this. In the golden rule, steady state, the marginal product of capital net of depreciation equals the population growth rate plus the rate of technological progress. Now let's discuss on the growth empirics. Solow model steady state exhibits balanced growth, that is, many variables grow at the same rate. That is, 1. Solow model predicts output per worker and capital stock per worker grow at the same rate G. If that's the case, then K over Y should be constant. That is, capital as a share of total output should be constant. And this is true in the real world. And second, Solow model predicts that real wage grows at same rate as output per worker, while real rental price is constant. And this is also true in the real world. Next, Solow model predicts that other things equal, poor countries with lower output per worker and capital stock per worker should grow faster than rich ones. If true, then the income gap between rich and poor countries would shrink over time, causing living standards to converge. However, in the real world, many poor countries do not grow faster than rich ones. Then the question is, does this mean the Solow model fails? Now let's look at it again carefully. Solow model predicts that, other things equal, poor countries with lower output per worker and capital stock per worker should grow faster than rich ones. So to answer the question, does this mean the Solow model fails? The answer is no, because other things aren't equal. That is, one, in samples of countries with similar savings and population growth rates, income gaps shrink about 2% per year. In other words, controlling for saving rate S and population growth rate N differences, there's convergence. Second, in larger samples, after controlling for differences in saving, population growth, and human capital, incomes converge by about 2% per year. Therefore, what the Solow model really predicts is conditional convergence. That is, countries converge to their own steady states, which are determined by saving, population growth, and education. And this prediction comes true in the real world. That is, the income gap between countries that are similar in observable characteristics appear to narrow over time. The differences in income per capita among countries can be due to differences in 1. Capital, either physical or human capital, per worker, and 2. The efficiency of production, that is the height of the production function, as both are implied by the Solow model. And studies found that both factors are important, and the two factors are correlated. That is, countries with higher physical or human capital per worker also tend to have higher production efficiency. There are three possible explanations for the correlation between capital per worker and production efficiency. 1. Production efficiency encourages capital accumulation. 2. Capital accumulation has externalities that raise efficiency. And 3. A third unknown variable may cause capital accumulation and efficiency to be higher in some countries than others. Now the question, is free trade good for economic growth? Since Adam Smith, economists have argued that free trade can increase production efficiency and living standards. And there are a couple of evidences that supports this. That is, first is research done by Sachs and Warner, which classified countries as either open or closed. They found that among both the developed and developing nations, the average growth rate for open countries is much higher than the closed countries, which confirms the theory that free trade is good for economic growth. And there's one more research we're going to look at that confirms this theory next. To determine causation, Frankel and Romer exploited geographical differences among countries. That is, some nations trade less because they are farther from other nations or landlocked, and such geographical differences are correlated with trade, but not with other determinants of income. Hence, they can be used to isolate the impact of trade on income. And they found that increasing trade per GDP ratio, that is, also used as a measure of economic openness, which is equivalent to absolute value of exports plus absolute value of imports divided by GDP. And increasing trade per GDP ratio by 2% causes GDP per capita to rise 1%, other things equal. Next on policy issues, that is allocating the economy's investment. In the Solow model, there's one type of capital. However, in the real world, there are many types, which can be divided into three major categories. That is, 1. Private capital stock, 2. Public infrastructure, and 3. Human capital, the knowledge and skills that workers acquire through education. How should we allocate investment among these types? There are two viewpoints. That is, 1. equalize tax treatment of all types of capital in all industries, then let the market allocate investment to the type with the highest marginal product. The second viewpoint is industrial policy, where government should actively encourage investment in capital of certain types or in certain industries because they may have positive externalities that private investors do not consider. By the way, this sounds good at first. However, there's a problem with this. And let's look at the possible problems with industrial policy next. The first problem is that the government may not have the ability to pick winners. That is, choosing industries with the highest return to capital or biggest externalities. And second problem that's possible is that politics, for example, campaign contributions, rather than economics, may influence which industries get preferential treatment. Next policy issue is establishing the right institutions. In economics, there are two kinds of institutions. That is, one, formal institutions, for example, law, and two, informal institutions like culture and norms. And creating the right institutions is important for ensuring that resources are allocated to their best use. For example, one, legal institutions to help to protect property rights. Protecting property rights is important because it increases the incentive to invest, which will lead to increase in capital that will lead to increase in productivity. Second, capital markets. The existence of capital market is important because it helps financial capital flow to the best investment projects. So it is important to have capital markets, and also it functions well. And finally, a corruption-free government is also important because it promotes competition and it helps to enforce contracts, etc., to reduce uncertainties in the society that enhances more economic interaction and productive use of resources. One of the best examples that demonstrates why establishing the right institution is important in increasing living standard is this: the stark contrast in economic development, growth, and progress between the North and the South Korea. After World War II, Korea split into North Korea with institutions based on authoritarian communism, and South Korea with Western-style democratic capitalism. Today, GDP per capita is over 10 times higher in South Korea than North Korea. At nighttime, you can see that South Korea is well lit, indicating the widespread access to electricity, versus North Korea is, except in Pyongyang, it is hard to find any light. Even with the same culture, same language, and same characteristics, after half a century passed, the differences in institutions made a huge difference in living standards between the two countries. Here I posted one of the most popular Introduction to Economic Growth textbook by Charles Jones and Dietrich Vollrath. They believed the satellite picture at nighttime of Korean Peninsula clearly demonstrate the importance of economic growth and where the difference may come from. Now let's quickly go through the next policy issue, which is encouraging technological progress. 1. Patent laws. So patent laws encourage innovation by granting temporary monopolies to inventors of new products. And second, tax incentives for research and development. Studies found that social return to research and development is greater than 40% per year. Therefore, many believe government should encourage research and development in general. And third, grants to fund basic research at university. Fourth, industrial policy. This encourages specific industries that are key for rapid technological progress. However, it is also subject to the preceding concerns that I listed before. Even though endogenous growth theory is very important in economic growth, I decided to focus on Unisono model in detail in learning how the model looks, the specification of the model, and the implication of the model. So here, I just want to focus on the basic differences between the two. In the Solow model, sustained growth in living standard is due to technological progress, where the rate of technological progress is exogenous. That is, it does not tell you what actually drives it. On the other hand, endogenous growth theory is a set of models where the growth rate of productivity and living standards is endogenous. That is, it tries to explain the behavior of the rate of technological progress and productivity growth, rather than merely taking these rates as given. Basically, endogenous growth theory may examine the determinants of the rate of technological progress, which Solow model, that is Solow, takes as given, and explain also decisions that determine the creation of knowledge through research and development. For example, much research is done by firms seeking profits, where A. Patents create a stream of monopoly profits, and B. Extra profit may come from being first on the market with a new product, and the resulting innovation produces positive externality that reduces the cost of subsequent innovation. In order to better understand the technological progress, so much of the new endogenous growth theory attempts to incorporate these facts into models. Finally, on economic growth as creative destruction, economist Joseph Schumpeter in 1942 coined the term creative destruction to describe displacement resulting from technological progress. That is, the introduction of a new product is good for consumers, but often bad for incumbent producers who may be forced out of the market. And the history confirms Schumpeter's thesis that there are winners and losers from technological progress. For example, Luddites who destroyed machines that displaced skilled knitting workers in England. Another example, Walmart, that displaces many mom-and-pop stores. These are good for consumers and for economic growth. However, it's bad for those people who lose their jobs. And the economy grows this so-called creative destruction process, according to Schumpeter.